Hello friends, welcome to my lecture on review of Z transforms. In this lecture, we shall discuss Z transforms and their properties. Let us first discuss the Laplace transforms, because Z transforms is a discrete analog of Laplace transforms. Laplace transforms are used extensively to analyze continuous time analog signals as well as systems that process continuous time signals. The Laplace transform is used to represent a large class of continuous time signals as a superposition of many simpler signals, sometimes called basis function or kernels. For signals that are 0 for negative time, the Laplace formula given by xs equal to integral over minus infinity to infinity x t e to the power minus s t dt is taken over positive time, giving the one sided or unilateral Laplace transform xs equal to integral 0 to infinity x t e to the power minus s t dt. For many linear not time invariant continuous time systems, the relationship between the input and output signals can be expressed in terms of linear constant coefficient differential equations. The one sided Laplace transform is a useful tool for solving these differential equations. For such systems, the Laplace transform of the input signal and that of output signal can be expressed in terms of a transfer function or system function. Many of the properties such as causality or stability of LTI system, that is linear time invariant system, can be easily explored by considering the system function of the continuous time system. Another property of the Laplace transform is that it maps the convolution relationship between the input and output signals in the time domain to a conceptually simpler multiplicative relationship. For discrete time signals, an analogous relationship is developed between signals and systems using the Z transform. The discrete time complex exponential signal z to the power n, where z is a complex number, plays a similar role to the continuous time complex exponential signal e to the power st. Discrete time signals of this form play an important role in the analysis of linear constant coefficient difference equations. For Z transform is a valuable tool for the analysis of discrete time signals and systems. As with the case of Laplace transform, the Z transform is a function of a complex variable. The transform itself can also take on complex values, hence it is a complex function of a complex variable. Let us first define a unilateral Z transform, that is one sided Z transform. So, the one sided or unilateral version of the Z transform is defined as follows. Suppose we have a sequence xn where n runs from 0 to infinity through the positive integers. So, n equal to 0, 1, 2, 3 and so on. So, when we are given a sequence xn, the unilateral Z transform of the sequence xn is defined as z xn equal to sigma n equal to 0 to infinity xn into z to the power minus n for all z such that the summation the infinite series in 1 converges. Here z is a complex variable and the set of values of z for which this sum converges is called the region of convergence of the Z transform. The Z transform maps the sequence to functions and their associated region of convergence such that z xn is the Z transform of the sequence xn. Now, let us consider the sequences for which the Z transform is defined. The sequences for which the Z transform is defined can be real valued or complex valued. The region of convergence will be all values of Z outside of some circle in the complex Z plane of radius r, the radius of convergence of the series 1 as shown in the figure below. So, the radius of convergence will be some region outside the circle of convergence of radius r which center at the origin, where r is given as the radius of convergence. So, here for example, the region of convergence is this shaded portion and it is outside the circle which center at origin and radius r in the complex Z plane. So, this region can be represented by mod of Z greater than r. Now, the uniqueness of the Z transform derives from properties of power series expansions of complex functions of complex variables. Let us consider the sequence x n equal to 2 to the power n, where n begins from 0 to infinity. So, then consider this sequence which is defined for non-negative integers n equal to 0, 1, 2, 3 and so on. So, here you can see in this figure these are the values of n when n is equal to 1, x 1 is equal to 2. So, we have this point 2, then at n equal to 0 we have n equal to 0 we have 2 to the power 0. So, 1, and then when we n we have for n equal to 1 we have 2, n equal to 2 we have 2 square, that is 4, n equal to 3 we have 2 cube, that is 8, and n equal to 4, that is here 2 to the power 4, which is 16, n equal to 0 you can see it is 1 here. Now, then let us find the Z transform of this sequence. So, the discrete time sequence has a Z transform given by Z of 2 to the power n equal to sigma n equal to 0 to infinity 2 to the power n Z to the power minus n. So, we can also write this as Z of 2 to the power n equal to sigma n equal to 0 to infinity 2 by Z to the power n. Now, this is a geometric series, and so its sum will be 1 over 1 minus 2 over Z, provided mod of 2 by Z is less than 1. So, mod of 2 by Z is less than 1 gives you mod of Z greater than 2. So, the sum of this series is Z over Z minus 2, provided mod of Z is greater than 2. So, mod of Z greater than 2 is the region of convergence of this series, and you can draw this region of convergence. So, this is your circle with center at origin and radius 2. So, this is mod of Z equal to 2, then the region of convergence is this. So, for this series region of convergence is mod of Z greater than 2. Now, in general Zxn is sigma n equal to 0 to infinity xn Z to the power minus n. So, in general Zxn converges for all Z that are large enough, that is when Z is sufficiently large that the signal xn Z to the power minus n becomes summable. Now, consider the sequence xn equal to a to the power n, where n is greater than or equal to 0, n is an integer. So, then this will be Z of a to the power n, a is any complex constant here. So, Z of a to the power n will be sigma n equal to 0 to infinity a n Z to the power minus n, and this can be written as sigma n equal to 0 to infinity a by Z raised to the power n. Now, again this is a geometric series. So, its sum is 1 over 1 minus a by Z, provided mod of a by Z is less than 1. So, this can be written as Z over Z minus a, provided mod of Z is greater than mod of a. So, the sequence a n has Z transform given by Z over Z minus a, where mod of Z is greater than mod of a. Now, we mentioned that the Z transform of a sequence, whenever we mention the Z transform of a sequence, we should also write the region of convergence of the series. Not only the expression of Zxn is to be given, its region of convergence must also be specified. Now, let us show that Z transform is linear. Okay. So, let x n and by n be any two sequences such that their Z transforms exist, then Z of a x n plus Z of a x n plus b y n is given by definition. Let us write it as sigma n equal to 0 to infinity a x n plus b y n into Z to the power minus n, and this can be written as then sigma n equal to 0 to infinity a x n Z to the power minus n plus summation n equal to 0 to infinity b by n Z to the power minus n. Now, sigma n equal to 0 to infinity x n Z to the power minus n is convergent. So, this is equal to a times sigma n equal to 0 to infinity x n Z to the power minus n, and we have b times similarly n equal to 0 to infinity b by n Z to the power minus n. So, since sigma n equal to 0 to infinity x n z to the power minus n and sigma n equal to 0 to infinity by n z to the power minus n are convergent, okay, we can write this sum, infinite sum, as sum of these two series, and then we can bring the scalar a and b outside. So, then this is a times z of x n plus b times z of by n. So, if we have two sequences x n and by n whose z transforms are known and a and b are any complex constant, then z transform of a x n plus b y n will be a times z x n plus b times z by n. So, that we can obtain it shows that z transform is a linear operation. Now, let us consider a sequence x n equal to n to the power p, where n is there in n and p belongs to n. So, z of n to the power p is equal to sigma n equal to 0 to infinity n to the power p z to the power minus n. Okay. Now, let us differentiate z of n to the power p. So, then what we get, summation n equal to 0 to infinity n to the power p into minus n z to the power minus n minus 1. Let us multiply both sides by minus z, then minus z d over dz of z n to the power p equal to sigma n equal to 0 to infinity n to the power p plus 1 into z to the power minus n. Okay. Now, right side is z transform of n to the power p plus 1. So, z transform of n to the power p plus 1 is given by minus z into d over dz of z transform of n to the power p, and this relation is called as the recurrence relation. Okay. If you know the z transform of n to the power p, you can find z transform of n to the power p plus 1 by differentiating z of n to the power p with respect to z and then multiplying by mod z. For example, let us find the z transform of n. Okay. Z transform of n, you can take p equal to if you take p, we have taken p as 1. Okay. So, z transform of n, if we want to know, z transform of n square we can find here. If we take p equal to 0, even for p equal to 0 it is true, because z transform of n we can find here. So, if you take p equal to 0 here, we get z of minus z d over dz of z transform of p 0. So, we get 1. Okay. Now, z transform of a to the power n we have found, z transform of a to the power n, where a is any complex number, we can take a as 1. Okay. Then 1 to the power n will be 1 for all n. So, we will have the sequence x n as 1 for all n. Okay. And that sequence we can consider. So, that sequence will then that gives you z transform of 1 equal to 1 over 1 minus z over z minus 1, where mod of z is greater than 1. So, this is equal to minus z d over dz of z over z minus 1, provided mod of z is greater than 1. So, then we can differentiate this, we can write it as z n equal to minus z d over dz of we can write it as 1 plus 1 upon z minus 1. So, then z over z minus 1 can be written as 1 plus 1 over z minus 1, we can differentiate this is minus z, and then we get minus 1 upon z minus 1 whole square. So, what we get is z over z minus 1 whole square. Okay. So, we get z transform of n, z transform of n is z over z minus 1 whole square. Now, we know the z transform of n, we can find the z transform of n square. So, z transform of n square will be equal to minus z times d over dz of z over z minus 1 whole square. So, when you differentiate z over z minus 1 whole square with respect to z and multiply by minus z, we get the z transform of n square, which is z square plus z over z minus 1 whole cube. Now, let us discuss a property of z transform. Another property, if z of x n is equal to x z, then z of a to the power minus n x n is equal to x a z, and a corollary to this result is z of a to the power n into x n is x of z by a. So, let us first show that if z of x n is x z, then z of a to the power minus n into x n is x a z. So, by definition, z of x n is equal to x z is equal to sigma n equal to 0 to infinity x n z to the power minus n. Now, let us multiply x n by a to the power minus n. So, then z transform of a to the power minus n into x n will be equal to limit sigma n equal to 0 to infinity a to the power minus n x n into z to the power minus n. Now, this right hand side can be written as sigma n equal to 0 to infinity x n z by a to the power a z to the power minus n, a z to the power minus n, and therefore, by our definition this is x of a z. Okay. So, z transform of a to the power minus n x n is equal to x of a z. Okay. Now, here if you replace 1 by a, then you get the corollary. Okay. So, replacing a by 1 over a in the above result, we get z transform of a to the power n x n equal to x of z by a. So, we get this corollary. Okay. Now, the geometric factor a to the power minus n, when mod of a is less than 1, damps the function x n, and that is why we call it as a damping rule. So, now if you use the damping rule, we can determine the z transform of the sequence n into a n, okay, because we know the z transform of n. So, recall that z transform of n is given by z over z minus 1 whole square. Okay. We know z transform of n equal to z over z minus 1 whole square. So, this is your x z. Okay. Sequence x n is n. Okay. Now, we want z transform of n into a to the power n. So, z transform of n into a to the power n, we can apply the corollary. Okay. So, z transform of x n into a to the power n is z x z by a. So, replace z over z by z over a in the expression for x z. So, we get z by a divided by z by a minus 1 whole square. Okay. So, this is z by a divided by z minus a whole square by a square. So, this a square comes here, and what we get a z divided by z minus a whole square. Okay. So, z of n a to the power n is a z over z minus a whole square. Similarly, z transform of n square a to the power n can be determined, because we now know the z transform of n a to the power n. Okay. So, we know the z transform, or we can apply we know the z transform of n square. Okay. We have to use that. Z transform of n square is z square plus z over z minus 1 whole cube. Now, we want the z transform of n square into a to the power n. So, we can apply the damping rule. So, let us recall that z of n square is equal to z square plus z divided by z minus 1 whole cube. So, this gives you z transform of n square a to the power n equal to, replace z by z over a. Okay. So, we can write that z transform of n square a to the power n is equal to z over a whole square plus z over a divided by z by a minus 1 whole cube. Okay. So, this will give you z square plus a z divided by z square divided by z minus a whole cube. This is z square plus a z divided by a square, and here we get z minus a whole cube by a cube. So, we get a z square plus a square z divided by z minus a whole cube. So, z transform of n square a to the power n is a z square plus a square z divided by z minus a whole cube. Now, we can find the z transform of sequence which is of trigonometric functions. Say let us say x n equal to cos omega n, where n is greater than or equal to 0. So, for this we can use the linearity of the z transform. Okay. Linearity of the z transform can be used to determine the z transform of x n equal to cos omega n. So, z of cos omega n is equal to, by definition, sigma n equal to 0 to infinity cos omega n z to the power minus n. Now, we know that cos z equal to e to the power I z plus e to the power minus I z divided by 2. Okay. So, we have sigma n equal to 0 to infinity 1 by 2 e to the power I omega n, okay, plus e to the power minus I omega n z to the power minus n. We put the value of cos omega n here. So, e to the power I omega n plus e to the power minus I omega n by 2 in z to the power minus. Now, e to the power I omega n can be written as e to the power I omega whole to the power n plus z to the power minus into z to the power minus n, and we are using linearity here. Okay. So, using linearity, this half comes out and we write sigma n equal to 0 to infinity e to the power I omega n into z to the power minus n. E to the power I omega n is further equal to e to the power I omega raised to the power n, and then we have 1 by 2 sigma n equal to 0 to infinity e to the power minus I omega raised to the power n into z to the power minus n. Now, this omega is a real quantity. Okay. This omega is a real quantity. So, what we have, let us recall that z transform of a to the power n. Okay. Z transform of a to the power n is z over z minus a, where mod of z is greater than mod of a. Okay. So, taking a equal to e to the power I omega. Okay. Taking a equal to e to the power I omega, because a here could be a complex number. So, we get the z transform of the first summation, z transform of this will be 1 by 2 z over z minus e to the power I omega, where mod of z is greater than mod of e to the power I omega, which is 1. Okay. So, mod of z is greater than 1, and second term will be 1 by 2. Similarly, a we now take e to the power minus I omega, and mod of e to the power minus I omega when omega is real is equal to 1. So, again when mod of z is greater than 1, z transform here will be 1 by 2, this will be 1 by 2 times z plus z over z minus e to the power minus I omega. Okay. So, what we get is this 1 by 2 z over z minus e to the power I omega plus z over z plus z minus e to the power minus I omega, and this is 1 by 2 times z minus e to the power I omega into z minus e to the power minus I omega. Here we have z square times minus z into e to the power I omega plus e to the power minus I omega, okay, z square minus and then we have this is equal to 1 by 2 z square 2 z square, this will be 2 z square. So, 2z square minus 2z cos omega e to the power I omega plus e to the power minus I omega is 2 cos omega divided by, here in the denominator we will have z square minus z times e to the power I omega plus e to the power minus I omega. So, minus 2 z cos omega, and then we have plus e to the power I omega into e to the power minus I omega, which is e to the power 0. So, that is 1. So, this 2 will cancel with this 2, and we will have z square minus z cos omega over z square minus 2 z cos omega plus 1. Now, this series this series converges when mod of z is greater than mod of e to the power I omega. So, mod of z is greater than 1, and this series converges when mod of z is greater than mod of e to the power minus I omega, which is also 1. Okay. So, here also mod of z is greater than mod of e to the power minus I omega, which is equal to 1. So, for both the series, okay, the region of convergence is the same, mod of z greater than 1. Okay. So, this is equal to z transform of cos omega n is equal to this, where mod of z is greater than 1. Okay. Now, let us similarly we can find the z transform of the sequence sin omega n when x n is equal to sin omega n. So, x n is 1 by 2 I e to the power I omega n minus e to the power minus I omega n, and we can write, as in the case of the cos omega n, we can write it as 1 over 2 I e to the power I omega raised to the power n, and minus 1 over 2 I e to the power minus I omega raised to the power n. Then z of sin omega n will be equal to 1 over 2 I using linearity, z transform of e to the power I omega minus 1 over 2 I omega a raised to the power n, and z transform of e to the power minus I omega raised to the power n. Okay. So, this is 1 over 2 I z over z minus e to the power I omega minus z over z minus e to the power minus I omega. Again this is we are applying here the formula z of a to the power n. So, this series the z transform of a to the power n is z over z minus a when mod of z is greater than mod of a. So, mod of z, for the convergence of this we have mod of z greater than mod of e to the power I omega, which is equal to 1, and for the convergence of the series here, okay, the region of convergence is mod of z greater than mod of e to the power minus I omega. So, this is equal to also 1. Okay. So, region of convergence is again same for both the series that occurs here and the series that occurs here. So, then this is 1 over 2 I, we can write z minus e I omega into z minus e minus I omega, that is z square minus 2 z cos omega, as in the pre-case of cos omega n we have seen, plus 1, and here we will get z square and here minus z square, that will cancel. So, here we will get minus z e to the power I omega, here plus z e to the power I omega. So, z times e to the power I omega minus e to the power minus I omega. Okay. Now, z of e to the power I omega, z times e to the power I omega minus e to the power minus I omega divided by 2 I is sin omega. Okay. So, we get z sin omega divided by z square minus 2z plus 1. Okay. And this convergence region of convergence is mod z greater than 1. Now, let us take the Dirac time discrete time impulse delta n. Okay. Delta n is defined as 1 when n is equal to 0 and 0 otherwise. So, z unilateral z transform here will be what, z transform of delta n, okay, will be equal to sigma n equal to 0 to infinity delta n z to the power minus n. Now, at n equal to 0 delta n is equal to 1. So, when you put n equal to 0 here, we get delta naught, which is 1, z to the power naught is also 1. So, we get 1, and delta n is equal to 0 for all values of n other than 0. So, delta n equal to 0 makes other terms 0, and therefore, z transform of delta n is equal to 1. So, delta n goes to 1 and 1 goes to delta n. The inverse z transform of 1 will be equal to delta n. Okay. So, z transform of delta n is 1 and inverse z transform of 1 is delta n. Now, another sequence for which we can apply the knowledge of an existing transform is the unit step function z transform of un. Un is equal to 1 for all n greater than or equal to 0, okay, and 0 when n is less than 0. So, we can apply the formula that we have already found for a to the power n sequence. We have seen that z transform of a to the power n equal to z over z minus a when mod of z is greater than mod of a. Okay. Here a is any complex constant. So, let us take a equal to 1. Okay. So, z transform of 1 to the power n, 1 to the power n is 1. So, 1 equal to z over z minus 1, okay, when mod of z is greater than 1. Okay. So, here the sequence un is actually a and un is equal to a to the power n, where a is equal to 1 for all n greater than or equal to 0, because other terms of the sequence are all 0. So, sigma if you find the z transform of un, it is equal to sigma n equal to 0 to infinity 1 x n is 1, or you can say un is 1 into z to the power minus n. Okay. So, this is same as z transform of the sequence 1. So, z transform of the unit step function is z over z minus 1, where mod of z is greater than 1. Now, let us consider the delay property. When a sequence is delayed by a positive amount, then we have z of y n minus k u n minus k equal to z to the power minus k y z. Here k is any natural number. Now, this we can easily see z transform of here we have y n minus k sequence, y n minus k u n minus k. This is equal to sigma n equal to 0 to infinity y n minus k u n minus k. Okay. When n is equal to 0, 1, 2 and so on, then u n minus k is 0 whenever n is negative. Okay. U n is, we have seen u n is less equal to 0, okay, when n is negative. So, here this summation will be reduced to sigma n equal to k to infinity, because if n is less than k, n minus k is less than 0. So, by u n minus k is 0. So, by n minus k u n minus k, and u n minus k now is equal to 1. So, we get here, and we also have z to the power minus n here. So, 1 into z to the power minus n we have. Now, replace n minus k y equal to j. Okay. So, when you do that, this is sigma j equal to 0 to infinity, okay, by j, and n is equal to k plus j. So, z to the power minus k plus j. So, we can write this as z to the power minus k is, we can write outside the summation, and sigma j equal to 0 to infinity, and we have y j z to the power minus j. So, this is z to the power minus k into z transform of y n sequence, okay. So, which is y z. So, z to the power minus k into y z, okay. So, we get this formula. This is the delay property of the z transform. Now, advance property, okay, when y n is advanced by an amount k. So, z of y n plus k u n we want to find, okay. So, z transform of y n plus k into u n, we want to find this, okay. So, this is sigma n equal to 0 to infinity by n plus k into u n z to the power minus n, okay. Replacing this we can write as, so this is when n takes values from 0, this is what u n is equal to 1, okay. U n is equal to 1 for all n greater than or equal to 0, okay. So, we get here sigma n equal to 0 to infinity by n plus k z to the power minus n, okay. Now, n plus k if I write as j, then what will happen? J will begin with n is equal to 0, okay. So, j will begin with k and go up to infinity, and here we shall have by j z to the power n is equal to k minus j. So, minus k minus j, okay. So, we shall write it as z to the power minus k times sigma j equal to k to infinity, it is j minus k. Okay. Okay, n is equal to j minus k, z to the power k sigma j equal to k to infinity by j z to the power minus j. Now, I can write it as z to the power k into sigma j equal to 0 to infinity by j z to the power minus j when I subtract terms from 0 j equal to 0 to k minus 1 by j z to the power j. Okay. So, this means that z transform of by n plus k u n is equal to z to the power k, and I replace this is z transform of by j sequence. Okay. Z transform of by n sequence it is. So, I write it as by z. Okay. Then we have here by z minus by naught minus by 1 upon z minus by 2 upon z square and so on minus z by k minus 1 upon z to the power k minus 1. So, this is the advanced property, z transform of by n plus k u n is z to the power k into by z minus by naught minus by 1 by z minus by 2 by z square and so on by k minus 1 z to the power k minus 1. So, this is what we get. Okay. Now, let us go to convolution property. So, one of the useful properties of the Z transform is that it maps convolution in the time domain into multiplication in the time domain. If you have two sequences x n and h n which are defined as 0 when n is less than 0, then the convolution of the sequences h n and x n is defined as by n equal to convolution of h n and by n gives another sequence which is given by by n equal to sigma m equal to minus infinity to infinity h m x n minus m. Now, in this case x n is equal to 0 when n is negative and h n equal to 0 when n is negative. So, here h m will be 0 as long as m is negative. So, this m will vary from 0 to infinity h m x n minus m. Because of h m, okay, sum will be 0, I mean terms will be 0 here so long as m is taking negative values. Now, x n minus m, okay, x n minus m will be 0 whenever n is less than m. Okay. So, this means that m is less than m is greater than n. Okay. So, this means that this is equal to sigma m equal to 0 to n h m x n minus m. Okay. So, if you assume that x n and h n are zeros for n equal n less than 0 negative integer values of n, then by n is equal to sigma m equal to 0 to n h m x n minus m, because if m is more than n, okay, m is more than n, then n minus m is negative. So, x n minus m is 0. Okay. So, now let us find the Z transform of by n. We are going to show that Z transform of by n is the product of the Z transforms of the two sequences x n and h n. Okay. So, Z transform of by n is sigma n equal to 0 to infinity by n z to the power minus n, and let us now put the value of by n. Okay. So, by n if you put by n will be equal to sigma m equal to 0 to n h m x n minus m. Okay. So, this will be by n is equal to sigma m equal to 0 to n h m x n minus m. All right. So, we have this gives you sigma n equal to 0 to infinity sigma m equal to 0 to n, okay, h m x n minus m z to the power minus n. Okay. So, this will be equal to Now, let us see m depends on n, right. So, this is your m equal to n. Okay. M varies from n is independent variables, n is here and m is here. Okay. So, m varies from 0 to n. Okay. M varies from 0 to n. Okay. So, we are taking this like this, and then I change the order of integration. So, I put it like this. So, if you do this, then we shall change the order of integration and we will get n varies now from m to infinity. So, this is can be put as n varies from m to infinity, okay, and m varies from 0 to infinity. Okay. So, n varies from m to infinity, m varies from 0 to infinity, and we have h m x n minus m z to the power minus n. Okay. This interchanging the order of the summation, we get this. Now, put n minus m equal to j. Okay. So, what we will have sigma m equal to 0 to infinity, and here we shall have n equal to n minus m equal to j. So, j varies from 0 and goes up to infinity. Okay. And we have h m x n minus m will be x j and z to the power minus j plus m, right. So, this will be equal to sigma m equal to 0 to infinity. We can now separate it. We have h m z to the power minus m, and then we have summation j equal to 0 to infinity x j z to the power minus j. Okay. Now, this is z transform of h n, this is z transform of x n. Okay. So, we get z transform of x n into z transform of h n here. Okay. So, this is the proof. So, Z transform, if we know the Z transforms of two sequences x n and h n, okay, then the Z transform of their convolution can be found. It is the product of their Z transforms. Now, this property of Z transforms is used in the solution of difference equations. Also, we use this property in the probability theory. Now, let us discuss the initial value problem per causal signal. So, let us say we want to prove that the initial value, the sequence we know is x n, the first term of the sequence is x naught, okay, x naught, x 1, x 2 and so on. Okay. So, we want to determine the initial value or initial term of the sequence, that is x naught. So, the initial value theorem says that the initial value of the sequence x naught can be found if we take n tends to infinity in z of x n. Okay. So, z of x n is what? Z of x n is sigma n equal to 0 to infinity x n z to the power minus n. So, this is x naught plus x 1 by z plus x 2 by z square plus, okay. So, limit z tends to infinity z x n, okay, is equal to x naught, because when z goes to infinity 1 by z goes to 0. So, these terms all will be 0, will tend to 0. So, x 1 by z, x 2 by z square, x 3 by z cube all will tend to 0. So, in the z transform of x n, when we take z to go to infinity, we get x naught. So, if the limit of z of x n as z tends to infinity exists, then it will give us the value of x naught, the initial value of the sequence. Now, so this is the proof. Let us go to next theorem, which is final value theorem for z transform. If z of x n is equal to x z and limit of x k as k goes to infinity, the final term of the sequence is x infinity. So, that is why we call it as a final value theorem. So, final value x infinity can be found, or limit of x k as k tends to infinity can be found from this formula, limit z tends to 1 z minus 1 into x z. Now, let us to prove this result, let us take the z transform of the expression x k plus 1 minus x k. So, z transform of x k plus 1 minus x k is sigma k equal to 0 to infinity x k plus 1 minus x k into z to the power minus k, and this can be written as, now this x k plus 1 minus x k we can write in this form, limit k tends to infinity n equal to 0 to k x n plus 1 minus x n into z to the power minus n. Now, here what is happening, we can now write this finite sum, this is a finite sum. So, we can write it as sigma n equal to 0 to k x n plus 1 z to the power minus n minus sigma n equal to 0 to k x n z to the power minus n. So, then what we will do, so we can write now this further as limit k goes to infinity, okay, and you put the values of n, and first term will be minus x naught, okay. Here you will get, when you put n equal to 0 you get minus x naught, when you put n equal to 0 here what you get x 1 z to the power minus 1, and here when you put n equal to 1 what you get minus x 1, here when you put n equal to 0 you get x 1 z to the power 0, okay. When you put n equal to 0 here we get x 1 z to the power 0, here you get minus x 1 z to the power minus 1. So, this is equal to x 1 times 1 minus z to the power minus 1. Similarly, we can put n equal to 1 here, you get x 2 z to the power minus 1, and you will get here n equal to 2, if you put you get x 2 z to the power minus 2, okay. So, this way we will get these terms. So, minus x naught x 1 z 1 minus z to the power minus 1, then the next term will be x 2 z to the power minus 1 minus z to the power minus 1, okay, like this. So, if we go like this, here what will happen, x l into z to the power minus l minus 1, okay. So, if like we had here x 2 z to the power minus 1, okay. So, we when you put here l, okay, x l z to the power we will have minus l minus 1. So, we will get this one x l z to the power minus l minus 1 1 minus z to the power minus 1, and then the term last term is this one, last term is x n plus 1. So, last term will be x k plus 1 z to the power minus k, and here what will get x k z to the power minus k, you get x k plus 1 z to the power minus k, and here you get minus x k, just a minute, x k plus 1 z to the power minus k, that is the last term, okay. And the term before that is when you put n equal to k minus 1. So, x k z to the power minus k minus 1, okay, and here what we get minus x k z to the power minus k. So, x k z to the power minus k times 1 minus z to the power minus 1 we get. Here when we put here n equal to k minus 1, so we got this, okay, and n equal to k here gives you this, okay. So, z to the power minus k minus 1 we write, okay. So, x k z to the power minus k minus 1 into 1 minus z to the power minus 1, this is the term here, okay, and here we have x k plus 1 z to the power minus k. So, then limit z tends to 1, z of x k plus 1 minus x k will give you limit z tends to 1, limit k tends to infinity minus x naught x 1 z to the power minus l plus 1 minus z to the power minus 1 and so on, x n plus 1 z to the power x k plus 1 z to the power minus k, and this will give you interchanging limits, limit k goes to infinity z to the power k goes to 1, limit z goes to 1 minus x naught plus x l z to the power minus l plus 1 minus z to the power minus 1 and so on, x k plus 1 z to the power minus k, and then when z goes to 1, these term will all go to 0. Okay. Those who contain 1 minus z to the power minus 1 as a factor, only these two terms will get this term and this term. Okay. So, but we will get limit k goes to infinity, this will become minus x naught, and then we have x k plus 1. Okay. So, what we get is this minus x naught limit k goes to infinity x k plus 1, this is the value of limit of z k plus 1 z of x k plus 1 minus x k as z goes to 1. Now, on the other hand, if you find z of x k plus 1 minus x k by the advanced property, let us apply this advanced property, this one. Okay. Z of by n plus k we have found, the z of by n plus k is z k into by z minus sigma m equal to 0 to k minus 1. So, here if you want z of by n plus 1, okay, take k equal to 1. So, z of by n plus 1, when n is greater than or equal to 0, u n is 1. So, we write u n as 1, then this is z to the power 1 by z minus when k is 1. So, m is 0. So, we get y naught z to the power naught. Okay. So, we get z into by z minus by naught. Now, in our case it is the sequence x n plus 1 x k plus 1, z of x k plus 1 will be z times x z minus x naught. So, we get this here. Okay. Z transform of x k plus 1 is z times x z minus x naught, okay, by the advanced property, and z of x k is x z. So, this is z minus 1 times x z minus z into x naught, this is z into x naught. Now, what we have? Okay. So, limit z tends to 1, z of x k plus 1 minus x k, okay. This will be equal to this value, when your z goes to 1, this value will tend to minus z x naught, okay, because this will tend to 0. So, limit z tends to 1, z x k plus 1 minus x k is limit z tends to 1, z minus 1 x z minus z x naught, which is limit z tends to 1 of this expression minus limit z tends to 1 of this expression. So, we get minus x naught plus limit z tends to 1. Okay, this will not go to 0 because x z may contain z minus 1 in the denominator. So, this is limit z tends to 1 z minus 1 x z. So, what we will get this value now can be put as minus x naught plus limit k goes to infinity x k plus 1. Okay. So, what we will have is, and limit of k plus 1 x k plus 1 as k goes to infinity is same as limit of x k. So, I can also write it as minus x naught plus limit k goes to infinity x k. Okay. So, this value is equal to this value, and therefore, this is equal to this. So, we get this result here, minus x naught plus limit k goes to infinity x k equal to minus this, and this implies that limit k goes to infinity x k is equal to limit z tends to 1 z minus 1 x z. Okay. So, this is the final value theorem. Now, let me take an example on this initial and final value theorem. Here we are given the z transform of a sequence x z equal to 2 z square plus 5 z plus 14 over z minus 1 to the power 4. We want to determine x 2. Okay. So, x 2 is let us look at the result. Limit k goes to infinity x k we have. Okay. So, limit in order to find x 2 we shall have to determine x naught first. Okay. The initial this one we will have to determine first. Okay. So, we have to go there. See, x z is what? X z is z transform of x n. Okay. So, this is sigma n equal to 0 to infinity x n z to the power minus n. So, this is x naught plus x 1 by z plus x 2 by z square and so on, x 3 by z cube and so on. Okay, let me find x naught first. X naught equal to limit z tends to infinity. Okay, yeah, we can do like this. See, x naught is equal to limit z tends to infinity x z. Okay, so this will be now limit z tends to infinity 2x z square plus 5z plus 14 divided by z minus 1 to the power 4. Okay. Now, in the denominator we have power of z 4, in the numerator we have power of z as 2. So, dividing by z to the power 4 in the numerator and denominator, we write limit z tends to infinity 2 by z square plus 5 by z cube plus 14 by z to the power 4, and denominator we have 1 minus 1 by z to the power 4. Okay. Now, when z goes to infinity, 1 by z goes to 0. So, we get 0. Okay. And then we find x 1, limit z tends to infinity. Now, what we will do, from x z we subtract x naught and then multiply by z. So, we get x z minus x naught, multiply it by z, then what we get x 1 plus x 2 by z, x 3 by z square, and so on. So, we can determine x 1 if we take the limit of this expression. So, x 1 is equal to limit z tends to infinity z times x z minus x naught. Okay. So, x 1 is equal to limit z tends to infinity z times x z minus x naught is 0. So, limit z tends to infinity z times again we put the value of x z 2 z square plus 5 z plus 14 divided by z minus 1 to the power 4. So, again we divide by z to the power 4. In the numerator the power of z, highest power of z is 3. Okay. So, we will have limit z tends to infinity 2 by z 5 by z square, and then we have 14 by z cube divided by 1 minus 1 by z to the power 4, and again we get the limit 0. Okay. So, x 1 is also 0. Now, we can find x 2. X 2 can be found if from x z we subtract x naught, then x 1 by z and multiply by z square and take the limit as z tends to infinity. So, x 2 is equal to limit z tends to infinity x z minus x naught minus x 1 by z. Okay. So, we subtract x naught, we subtract x 1 by z and then multiply by z square and take the limit as z tends to infinity. So, we will get x 2. So, this is now limit z tends to infinity. Now, x naught is 0 here, okay. X 1 is 0 here. So, we get limit z tends to infinity x z, and you can see here x z multiply by z square here. Okay. So, we have to multiply by z square. Okay. So, limit z tends to infinity. When you multiply this expression by z square, the power of z 4 becomes 2. In the denominator, power of z 4 is 1. Okay. So, we get, when you divide by z to the power 4 in the numerator and denominator and take the limit as z tends to infinity, we will get the limit as 2. So, this is z square. After you multiply and divide by z to the power 4, you get 2 plus 5 over z, okay, and then you have 14 over z square divided by 1 minus 1 by z to the power 4, and then you take the limit as z goes to infinity, you get the limit as 2. Okay. So, answer is 2 here. Okay. X 2 is 2, and now we have to determine x 3. So, again what we will do, we subtract from x naught, we subtract from x z x naught, x 1 by z, x 2 by z square, and then multiply by z cube. Okay. So, in order to determine x 3, we have x 3 equal to limit z tends to infinity z cube x z minus x naught minus x 1 by z minus x 2 by z square. Okay. So, this is limit z tends to infinity z cube x z is this 2 z square plus 5 z plus 14 divided by 5 z 2 z square plus 5 z plus 14. Z minus 1 to the power 4. X naught is 0, x 1 is 0, x 2 is 2. So, minus 2 by z square. Okay. X 2 is 2. So, this gives you limit z tends to infinity z cube into 2 z square plus 5 z plus 14 minus 2 times z minus 1 to the power 4, okay, which is equal to limit z tends to infinity z times uh, 2z square plus 5z plus 14 minus 2 times z to the power 4 minus 4z cube plus 6z square minus 4z plus 1. And here we will multiply by z square. Here we will multiply by z square. So, we have this is equal to limit z tends to infinity z times 2z to the power 4 will cancel with 2z to the power 4. We have 5z cube here and here we have 8z cube. So, 13 z cube and we have 14 z square minus 12 z square. So, 2 z square. 2z square plus 8z minus 2 divided by z minus 1 to the power 4. Okay. So, this is equal to limit z tends to infinity. When we divide by z to the power 4, we get 13 plus 2 z cube by z to the power 4. So, 2 by z plus 8 by z square, 8 by z square minus 2 by z cube divided by 1 minus 1 by z to the power 4. So, when z goes to infinity, the limit comes out to be 13 and therefore, the value of x 3 is equal to 13. So, x 2 is 2, x 3 is 13. So, this is the example on the initial and final value theorem. With this, I would like to end my lecture. Thank you very much for your attention.